don't think I'm muting you. I think you can unmute yourselves if you want to. This meeting is being recorded. And I wanted to know, I posted these notes on probability last night around 9 o'clock. And did I just pick the wrong? That's what I want. And so I'm sure we want to talk about these notes. Do we want to talk about the fundamental counting principle, the first section of notes? Do we want to talk about homework questions as well? Do we have questions about chapter 8? So let me know what you need. And this took about like 20 minutes in first period, these section of notes probability. So any requests?
Can we go over the section before this?
Sure.
Okay.
Okay. Anything else? Okay, so is the best use of our time to go over that section first and then this one? Or this one first and then that one?
The last one first and then this one.
Okay, so section 1, so the fundamental counting principle and then this one? Am I understanding that correctly? So we want to talk about this one first and then this one second.
Sounds good.
Okay, thanks. All right, so I think we have everybody that asked for the code. Okay, so the first section of notes that I posted is about the fundamental counting principle, factorials, permutations, and combinations. And so the essential questions are, what is the fundamental counting principle and when do I need it? Question 33 is, what is a factorial and when do I use it? Question 34 is, what is a permutation? And give examples of situations that require a permutation. And question 35 says, what is a combination and how is a combination different from a permutation? So that's what we'll be talking about in this section of notes. In the topic of probability, an event is quantified by the number of ways or outcomes the event could occur. So for example, a coin toss has 2 outcomes, either heads or tails. And the fundamental counting principle states that if one event can occur m different ways and a second event has n possible outcomes, then the number of outcomes of both events together is their product, m times n. So you can expand on this because it's true if there's 3 events or 4 events or 17 events, this idea of the product of the outcomes holds no matter how many events you have. So there's more about that on page 570. Our first example here from 10.1 example 1 says that if you flip a coin and roll a 6-sided die, how many outcomes are there? So the first event is the coin toss, and as we said, that's got 2 outcomes. The second event is rolling the die with 6 possible results. So using the fundamental counting principle, we would multiply them to get 12 outcomes. Does that make sense? Does that make sense? Is that okay?
Yes.
Yes.
All right.
Yes.
Okay, sounds good. Michael. Oh, thanks. Hold on. Give me a second. Oops. Shoot. Okay, so um, okay, there we go. Okay, so does that part make sense? We said yes, we're okay with that? Okay, so 10.1 example 1, we're a plus, so I kind of expanded to show the different number of events. So assume that your favorite color is green and that if you have 2 hats, 7 shirts, 5 pair of pants, and 3 pair of shorts in complementary shades of green with coordinating patterns. So even in a lockdown, we're not trying to have paisley and plaid here. So how many outfits do you have to choose from? So we've got 2 hats or no hats. 2 hats or no hats is an option, so that gives us 3 possible outcomes. And then 7 shirts, that gives us 7 outcomes because no shirt is not an option on this family program. And then 5 pair of pants or 3 shorts, so that's 8 possibilities, and we're assuming that the weather permits shorts, so we don't have to think, you know, it's 95 degrees and you'd only wear shorts, or it's 42 degrees and you'd only wear pants. So because they didn't specify that, we're assuming that pants or shorts are equally possible. So according to the fundamental accounting principle, we've got the hat or no hat option, the shirts and the bottoms to get 168 possible outfits. Does that make sense?
Mm-hmm.
Okay. All right. So n factorial is written n exclamation point, and it indicates the product of whole numbers. So n has to be a whole number. There won't be any fractions or decimals here. It's either 7, not 7.2. That's not a thing. So whole numbers from n down to 1. So n factorial equals n times n minus 1 times n minus 2 times n minus 3 and n minus 4, all the way down until the n is exhausted. Okay, so I know that kiddos don't love this explanation, so I put a hard value in there, a constant. So if we've got 4 factorial, that's 4 times 3 times 2 times 1. That gives us 24 possibilities. So also 0 factorial equals 1 always. That's not just an algebra 2 rule. That's true in college stats as well. Are we okay with that part? Do you know where to find the factorial button on your calculator? So on my calculator, I have this probability, this PRB button. So if I put in 8 and then I hit probability, and you can see the exclamation point is the third option. So I just arrow down to that. I hit enter. I hit enter again, and I get 40,320. Is that okay?
Yeah.
Anybody having an issue finding that button on their calculator? We're all good? Okay, great. So the next example that we want to talk about. So a permutation is an arrangement of objects in which the order is important, such as a password. So I would circle the P for password and the P for permutation so that I have a mnemonic device for remembering what they are. So the number of permutations of n objects taken n at a time is n permute n, which is just n factorial. Ava is trying to get in, but it's not letting her. Okay. I can't see that Ava's trying to get in. So I'll send her the code again. Oh, no, shoot. That's the wrong thing. Right? I don't understand why I haven't locked the meeting. Okay. I don't know why Ava's not able to get in. Okay. Should I keep going then? I mean, we're recording this, so maybe Ava gets to watch it later. I don't know what to do. I don't know how to fix this.
Miss Nemeth,
Yeah.
could you go over the calculator part one more time?
Yeah, the factorial?
Yeah. Or the one with the PRB button.
Yeah, so this button right here.
Mhm.
So when I push that, I have three options. There we go. I have the permutation button is that first option, the NPR. And then the second is the N choose R. And then the third option is the factorial.
And then do you like hit which one you want and then you plug in the number?
Well, okay, so if I'm going with a factorial, then I put in the number and then I choose the probability and then I scroll down and I hit enter and that would be a problem, right? Okay, so, but if I have 8 objects and I want to put them in different password orders, then I would choose permutation. And let's say I want a 4-letter password, but I've got 8 characters to choose from. So it turns out I have 1,680 possibilities. Does that make sense?
And that's when you're doing the NPR one?
Yes. So you have to put the number that's N to the left. You put that in first. You choose this, and then the number
got
that's R you put
Okay.
in second. Does that make sense?
Yes. Thank you.
Okay, cool. Other questions about that part? All right. Okay, so yeah, so the number of permutations of n objects. So n is the total you can select from. And then R is a subset of the total. So that's what it says. R has to be less than or equal to N is NPR. And this is the actual formula. Now, I don't really want you to know the formula. I want you to know the buttons on your calculator. Does that make sense? So again, N has to be larger than the subset, right? Because the total, and then you're taking sum of the total. So this is the larger number, this is the smaller number. That's the formula. And I showed you the button on your calculator. So here's this example. You manage a co-ed baseball team, the stay-at-homers, with 13 players. How many batting orders are possible if all 3 pitchers bat? So we've got 13 possibilities to bat first and 12 possibilities to bat second. 11 players that can bat third. So this is like the fundamental counting principle with diminishing possibilities, right? So this is a factorial. So 13 factorial equals 6,227,020,800 possible batting orders for your 13-player team. Are we okay with that? All right. So part A says, how many batting orders are possible if you want Flynn to bat third, followed by Blake and then Casey? So I have 13 players, but 3 of those batting positions, I know exactly there's just one player I want to bat third, one player to bat fourth, one player to bat fifth, right? Okay, so that means I have 13 players on my team, but those 3, I know where they want to bat. So that gives me 10 factorial, which is 3,628,800 possible batting orders. Is that okay? So your silence means we're good and I should keep going?
Yeah, it's good.
All right. Yeah? Okay. All right, so in 10.5 example 1, how many different permutations are there of, and I just came up with these 3 composers. So Bach has 4 letters in his name. They're all distinct and unique letters. None of them repeat. So 4 different letters gives us 4 factorial, which is 24 permutations, right? Mozart has 6 letters. They're all distinct. So 6 factorial is 720 permutations. Now keep in mind, if I use 6P6, I still get 720. Beethoven has 9 letters, but these 3 E's are repeated. So that means that we'll overcount because of the E's. They're not distinct or unique, right? So because factorial we do with multiplication, the only way to remove those overcountings is by dividing. Does that make sense? So the factorial is going to be 9 times 8 times 7 times 6, but 3 of them were overcounting, so we have to divide by that amount. So we end up with 60,480 permutations of the name Beethoven, of the letters of the name Beethoven. Are we okay with that?
Yeah.
All right. Okay, so we're ready for a combination. So a combination is a selection of objects in which the order does not matter, like a hand of cards. So if you've got a hand of cards, it doesn't matter if the queen is on the left of the cards you have in your hand or on the right. You still have the same playing power in the game, no matter where the queen is in your hand. So I tend to circle the C from cards and the C from combination, just so I have that mnemonic device of which is which. And I've outlined here for you what's in a deck of cards in case your family doesn't play cards. So there's 2 red suits, the hearts and the diamonds. There's 2 black, the spades and the clubs. And each suit has 13 cards from ace all the way up to king. So you'll be expected to know that for some of our questions. So 10.5 example 2, 10 horses are running in a race. In how many ways can there be a first, second, and third place if there are no ties? So we've got 10 horses, so that's our total, n equals 10. We're considering the first, second, and third, so r equals 3. Now it comes down to, is this a permutation or a combination? And it's a permutation because the order in which the horses cross the finish line is important. So because like third place and first place are not the same. So in this case, we've got 10p3, which is 10 factorial over 10 minus 3 factorial, which is this. But again, we're just using the calculator to put in 10 and then choosing, looks like this. So we put in 10, the probability NPR 3 gives us the 720. Are we okay with that part? Okay, so nobody has any questions. You would tell me if you had questions, right? All right, so the number of combinations of n objects taken r at a time. So again, n is the total, r is a subset of the total, is n choose r, and this is the formula. Again, it's read as n choose r, and there's a button on your calculator. I showed you where that is. I'll show it to you again in a second. So 10.5, example 4-ish, I'm asking you, how many combinations are there of the cards? The 2 of diamonds, the 4 of spades, the 7 of clubs, and the 8 of queens, the queen of hearts. And so there's only one way you could get those 4 cards, right? Because they're cards and the order doesn't matter. So does that make sense? Right, you're not talking to me. Okay. So in 10.5, example 5, if you order a sandwich to go, of course, and you have 8 side dishes to choose your 2 sides, notice that the order of the sides doesn't matter. So this is a combination, not a permutation. So 8 choose 2 is 8 factorial over 8 minus 2 factorial times 2 factorial is 8 factorial over this whole thing, which turns out to be 28 combinations. Are we okay with that?
Is n always greater than r?
Yes, otherwise your calculator will tell you 0.
Okay.
Yeah, it doesn't say domain error, which is, at least mine doesn't say domain error. It just says 0 is the answer, which is kind of sad. I like it when it says domain error because then I know I've done something wrong. 0 seems like, oh, okay, possible answer. Okay, so do we have other questions on these notes?
I had a question on the homework.
Okay.
Can you go over number 6 for me, please?
Oh yeah, so 6, it should be P4. I had P5 there, I don't know why.
Oh, okay.
Is
okay,
that your whole question?
Yeah.
Yeah, my glaring typo. Does anyone else want to hear number 6? Okay, so it should be, there's 4 people being selected to the committee, and I had like 12 P5 originally. So I found that typo the other day and I fixed it, but then I didn't update posting it. So sorry about that.
Thank you.
You're welcome. Okay, anything else from that part? We're okay with those notes and those homework? So we're ready for these notes? Okay, so hopefully you printed these out, but either way, it'll be fine. So here we're talking about probability. In the previous section of notes, we were using the counting principle and combinations and permutations, and we were getting pretty large numbers. In probability, we want to know the likelihood that something could happen. So our answers are going to be small numbers, fractions, decimals, percents less than 100, fractions between 0 and 1. So the probability of an event is a measure of how likely it is that the event will occur. So the probability of event A, which we write P of A, could be 0, which means that event A will not occur, or any value up to and including 1, which indicates that event A is guaranteed to happen. So all of our answers for probability should be between 0 and 1. 0 is a possible answer, 1 is a possible answer. If I ask you the probability of something and you say 740, that's not right. Does that make sense? Okay. So we will be studying theoretical probability as opposed to experimental probability, which would happen in a stats class. And the probability of event A is denoted P of A. So our essential questions, what is probability and what is the range of possible answers for a probability question? What cards are in a standard deck of 52 playing cards? How many possible outcomes are there for 2 6-sided die? And question 39, what is the probability of the complement? So 10.1 example 1 says, what is the probability of flipping tails when you toss a coin and then rolling a 3 on an 8-sided die? So I've got part A is what is the event? Part B is what is the solution method and why? And then part C is your answer reasonable? So part A, the first event is flipping tails. So I've got the probability of tails. And the second event is rolling a 3. So I've got the probability of 3. So because there are two events here and the probability of tails has a probability of 1/2. Remember, 2 represents you could flip either heads or tails. And P of 3 is 1/8 because it's an 8-sided die and 3 is one of those sides. I will use the fundamental counting principle to multiply the two probabilities to get a result of 1/16. So part C says the probability of these two events is between 0 and 1, so this answer is reasonable. Are we okay there? Okay, so no questions. All right, so our next example says to develop talent, the jazz band teacher randomly selects the first chair, the second chair, the third chair, etc. for the first class of every month. If you are one of 5 alto sax players, what is the probability that you will be selected for second chair? So part A is what is the event, part B is what's the solution method and why, and part C is your answer reasonable? So the event is the probability that you'll get selected second chair. There's only one way this could happen. You get selected for second chair or you don't. So we don't care about any of the other musicians in this case. So part B tells us, hold on a second. Okay, so part B says the direction state randomly selects the first chair, the second chair. So this randomly selects tells me that it's going to be like a factorial, because every time I select someone, then I've got fewer options for the number of musicians that could be in the subsequent chair. So in this case, the total outcomes in the denominator is 5, or 5 factorial. 5 factorial. So the probability that you're selected second chair is 1 out of 5 factorial, which is 1 out of 120. We're okay with that?
Miss Nina,
Okay. Yeah.
where does the 5 come from?
Because there are 5 alto sax players.
Oh, okay. Okay. Thank
If
you.
there were 7, then it would be 7 factorial.
Right. Okay. Thank you.
Sure. Okay, so since 1 out of 120 is between 0 and 1, this is a reasonable answer for a probability question, though it doesn't seem very likely that you'll get selected second chair. Okay, are we okay with that? All right. The theoretical probability of event A is the outcomes in that event that we want to have happen compared to the total number of outcomes that are possible. So that's why we wanted to be second chair. There's only one way that can happen, but it's possible that we could end up in any of the seats. So that's where the 5 factorial comes in. Okay. All right, so if we're ready for our next example. So given letter tiles that spell out seeking, what is the probability that you randomly select S and then E from the 7 tiles? So part A is what is the event, part B is what is the solution method and why, and then part C got left off, but it's checking the reasonableness of our answer. So part A says the event is selecting the S and then the E. So I've got the probability of choosing S, comma, then E. There's only one way this could happen because I don't have any other S or E in the word. So I would choose the S first, I would choose the E second, or I don't. So part B says, because the order matters, we have to use a permutation instead of a combination. I can't spell the word if I choose the E first and the S second. It won't work. So I've got 7 letters in the 7 tiles that spell out seeking. So, and I'm choosing 2 of them. So, so the probability of choosing the S and then the E is 1, that I choose the S and then the E out of 7 P2 options, which is 1 out of 42. So this answer is reasonable because it's between 0 and 1. Are we okay with that part? Okay, so you can see in the left margin here, I've laid out what's in a standard deck of playing cards again, just because kiddos don't always know. And 10.5 example 6 says, given a standard deck of 52 cards, what is the probability of drawing 2 face cards? So part A is what is the event, part B is what is the solution method and why did we choose it, and C asks if your answer is reasonable. So part A, the event is drawing 2 face cards, so a jack, a queen, or a king. So that's the probability of 2 faces. Since there are 4 suits, the hearts, the diamonds, the spades, and the clubs, and 3 face cards, that's 12 outcomes that we want. So because we are drawing cards, the order doesn't matter. So drawing a queen, then a king isn't different than drawing a king and then a queen. So we use combinations here instead of permutations. So we've got 12 options, we're choosing 2 of them. And that's for the desired outcome in the numerator. We've got 52 cards in the deck, we're choosing 2 of those, and that would be the total outcomes in the denominator. So the probability of 2 faces is 12 choose 2 over 52 choose 2, which is approximately that. But I want to show you how to type this into the calculator. So if you have your calculator handy, that'd be great. So I need to put in parentheses, 12 choose 2, close parentheses, divided by parentheses, 52 choose 2. And that's where I got my 0.05, approximately. Are we okay there? Okay. So checking our answer, yeah, that this answer seems totally reasonable, but it does not seem like it would be very likely that if you have a deck of 52 cards, the first 2 you choose would both be face cards. Okay. All right, so when rolling 2 6-sided die, there are 6 times 6 or 36 possible outcomes. Notice that's the fundamental counting principle right there. And I've included the illustration, though there is one also in your book on that page. So I wanted to remind you that from geometry, there are complementary angles. So if angle A is 73 degrees, then its complement is 90 degrees minus 73 degrees, or 17 degrees. So that same thing happens in probability. The probability of the complement of event A is P of A bar equals 1 minus P of A. And A bar is read A bar. So in Algebra 2, we will use the complement to make solving problems easier, which means you do not have to use this method if you don't want to. Also, since the maximum value for a probability is 1 or 100%, then we're subtracting all of the things that are not in that case to find the probability here. So like complementary angles is 90 degrees because that's the full angle. So here it would just be 1 because that's the full possibility for a probability. Okay, so are we okay so far? All right. So 10.1 example 3, we have to find the probability that the sum of 2 6-sided dice is not 6. So part A, what is the event? Part B, what's the solution method of Y? And part C, is the answer reasonable? So part A, the event is the sum doesn't equal 6, but there are a lot of these combinations that don't equal 6. So we could count those up and put them out of 36 if we wanted to, or we could use the complement of the event. So what's the probability that the sum is 6? which has only 5 pairs, 1 and 5. You could roll a 2 and a 4, a 3 and a 3, a 4 and then a 2, or a 5 and then a 1. So the probability that the sum is not equal to 6 is 1 minus the probability that the sum does equal 6. So I have 1 minus 5 over 36, which simplifies to 31 over 36. So our answer is between 0 and 1, so it's reasonable for a probability question. And this is a pretty high, so it seems much more likely if you roll 2 die that they won't add up to 6. So any questions about that? Okay. So if we don't have any other questions, calculator questions, we're pretty much done, I think, unless you have other topics you want to talk about. Okay, so you are welcome to leave the meeting, and I will hang out here in case anybody has other current events, philosophy questions they want to ask me.